So now that we've defined what a triangle is, we're going to talk a little bit more about classifying triangles. One of the most basic things we like to do when we set up a new definition of something is to see what properties it has in general. But then next, we like to look at maybe some subclasses of that and see what special properties things in that subclass might have. So this idea of just sorting things is a pretty natural human activity that we do a lot in mathematics. And we like to establish some hierarchical subset structure among these various subclasses. So first of all, let's look at properties that all triangles have. And this is regardless of which geometry we're talking about being in. They have three sides, which are line segments, three vertices, that's where the points where the sides meet, or the endpoints of the sides, three interior angles. Of course, each is the union of two rays with a common vertex. Um, and that vertex is a vertex of the triangle, and each angle contains two sides of the triangle. Each triangle is contained in exactly one plane. That's a good little proof for you to try to do, not hard. If triangle ABC equals triangle DEF, then the set ABC and the set DEF are the same. In other words, it only has three vertices. This D, E, and F must be A, B, and C in some order. If a line in the plane of a triangle intersects one side of the triangle, then the line intersects at least one other side of the triangle. If a line in the plane intersects one side of a triangle does not contain a vertex of the triangle, then the line cannot intersect all three sides of the triangle. And we'll define these terms later, but eventually we'll see that a triangle is a convex polygon with three sides. It's a closed plane figure, and it has a finite area and a finite perimeter. We may be able to say something general about the relative sizes of the angle measures, but this may vary from geometry to geometry. So these are the things that we can say right now about all triangles. So how would you go about classifying a triangle? What are some interesting properties that some triangles have that others do not have, by which they can be sorted into groups? Okay, little subgroups of triangles. So see if you can think about this. Pause for just a second and then come back and we'll check your answers. Pause. Okay, well, there's not a lot to triangles. There's just three sides, three angles. Um, and that's basically what we could do. We could classify them by the size, about the three sides and the three interior angles. Okay, by the lengths of the sides and the measures of the interior angles. And we have a few definitions. Remember, we've already defined what we meant by congruent sides, the line segments with equal length, and congruent angles, the interior angles, the equal angle measures. So we can classify them by congruent sides, the number of congruent sides. A triangle is a scalene triangle if and only if it has no two sides that are congruent. So all three sides are different lengths. A triangle is an isosceles triangle if and only if it has at least two congruent sides, two sides the same length or more. A triangle is an equilateral triangle if and only if it has all three sides congruent to each other, all three sides the same length. We can also classify by angles. A triangle is an acute triangle if and only if all of its interior angles are acute angles. A triangle is a right triangle if and only if it contains a right interior angle. In a right triangle, the sides that are included in the right angle are called the legs. Non-right triangles are called oblique triangles. A triangle is an obtuse triangle if and only if it contains an obtuse interior angle. A triangle is an equiangular triangle if and only if all three of its interior angles are congruent to each other. And a triangle is a regular triangle if and only if it is both equilateral and equiangular. Ultimately, we'll talk about a regular polygon as one that is both equilateral and equiangular. Notice the at least part here on isosceles. So since that says at least, right, two congruent sides, that means an equilateral triangle is a subclass. The class of equilateral triangles is a subclass of the class of isosceles triangle. Every equilateral triangle is isosceles triangle, but not every isosceles triangle is equilateral. There are several advantages to a hierarchical system like that we'll talk about a little bit later, especially when we start talking about classifying quadrilaterals. Right triangles are a particularly important class of triangles which are studied extensively in trigonometry. And we can combine these two classifications to obtain what are, at least in Euclidean geometry, 6 non-overlapping categories of triangles, along with equilateral triangles, a seventh subclass of acute isosceles triangles. And so here's a table that we're going to contain illustrations of some of these right here. So these are scalene triangles, different size, all different size lengths. These are isosceles, as is this one, and that's equilateral. All of these are acute triangles. The first row, the middle row, they're all right triangles, and they're all obtuse triangles in the bottom row. So this is an acute scalene, acute isosceles, right scalene, obtuse scalene, obtuse isosceles, and if it's equilateral, it's automatically an acute isosceles triangle as well. It cannot be a right or an obtuse triangle. Now here I have an activity I want to take a quick look at that I've put together. Okay, and this one is on classifying some triangles. Okay, here it is. As usual, I like to open these in the app. Okay, and here's that same table that we just looked at. So, first of all, here's a general triangle. Here's the definition. And you can see it's a general triangle. We can move these vertices anywhere we want here. And we see the sides and angles measured there. Here's an acute triangle. We move this around. It stays an acute triangle. And we can get basically any acute triangle here. If you notice, all the angles has this little orange point's a control point too, as well as the vertices. So that one stays acute. This one stays a right triangle. Some of these are really easy to build and some are not quite so easy. Okay, we notice you always get a right angle there. I'm measuring everything in degrees on this particular one. We could switch it to, if we wanted to, we could go over here and go to settings and switch to radians if we'd rather. For now, I'm going to stay in degrees. Okay, here's an obtuse triangle. This is set up so that this angle has to be 91 degrees or larger. And then this can be moved out so that the other angles stay to be, so that we always have an obtuse triangle out of it. This one's scalene. All the sides have to be different lengths on this one. Well, the way I built this one, actually, this distance xy, this green distance, has to be greater than this xz, this blue distance. It may be possible, if you work hard at it, that you could get this red distance to either match the blue or the green. So it may not be perfectly always a scalene, but I think most of the time it will be. It's going to be very hard to make it not be a scalene triangle. All the sides different. Here's an isosceles triangle. The two red sides are the same. Notice we've marked them the same color, but also with the little hash mark there. Notice something interesting about an isosceles triangle that we noticed. Look at these two angles down here. Now they'll be different depending on where we put it, just like these lengths may be different, but these two are the same length as each other. Isosceles literally means two sides that are congruent, two sides are the same length. But we could have also said it, well, it's just two angles that are the same length. We'll prove later on that it's an isosceles triangle if and only if it has a pair of congruent angles, base angles here. The angles opposite the two congruent sides are actually congruent. One thing that we find in general for a general triangle is that the smallest angle here is opposite the shortest side, and the largest angle measure there is opposite the largest side. Of course, the one in the middle is in the middle there. An equilateral triangle here in Euclidean geometry always has angles that are all three the same. They're all angles of measure pi over 3 or 60 degrees, and all sides are the same. And it turns out this is an if and only if two. If it's all equal angular, it has to be equilateral. If it's equilateral, it has to be equal angular. Either one, that means it's a regular triangle. Now, if we put some of these together, this one's both acute and scalene. This one is right and has to be scalene. You notice that you go as far as you can. It's just a little bit longer than that one, but you can go on up. This is obtuse and scalene, obtuse angle. This will help adjust the angle there. Like that. Obtuse and scalene. Next one is acute and isosceles. So now all three angles are acute angles, and it's an isosceles. A right isosceles there. And obtuse isosceles here. So we get to see every one of the different kinds again, and then there is the classification table for it. Here are a couple of other activities. These were, I think, created by the GeoGebra team. I tried to keep their GeoGebra team activities in my book that I have here for triangles, or for geometry in general, collected resources. So this collects my activities, like this one and this one, but also the ones here by the GeoGebra content team. So let's see what this one is about. So basically you can move these around to get what's called a lattice polygon, a lattice triangle. That is, you have a grid here, and the vertices are on the grid lines. This is the same as taking rubber bands and putting them on a device called a geoboard, which is just pegs on each one of these. So the idea is we can look at this here, and if we click on things, this is an acute triangle there, and if we click on the sides, the three sides are not congruent, none of them, so it's a scalene triangle. And we could just say, okay, try to make something, like try to make a right triangle. So there's a right scalene triangle. Okay. And then that one's scalene. What about right isosceles? Can we do that? Let's see. Are we there yet? Let's see. That one looks like that might be it. Yeah, those two are the same, so that's isosceles. So that angle and that angle are the same, 45 degrees, power 4. That one's power 2, or 90 degrees in measure. And so forth. And so you can just kind of play with that a little bit. It gives you some questions here that you might work on as well. So that's one that the GeoGebra team put together. That one and the last one that I made are really good for elementary students or middle school students, as well as for college geometry students or high school geometry students. Okay, so this is kind of a test. Is that an acute? That's an acute one, looks like. So we can check it, correct. See what we want to do. A scalene. That's scalene. Let's check it out. Isosceles. That ought to do it. Obtuse. There's one. Right. How about there? And so you can just keep going through these different ones and sort of testing yourself. So these are again, excellent activities for a person just getting used to this. Here's one more. Now this one is one that I made. And this one we're going to be going into um, not only Euclidean geometry, but hyperbolic and taxicab geometries as well. So, but specifically looking at let me open in the app. But specifically, we're going to be looking at isosceles triangles and all three. And the way you build them in GeoGebra is you start by building a circle by center and point to get the points A and B, which are free to move anywhere we want them. And then C is just another point on the circle. And then you finish up with the line segments. So that is an isosceles triangle that is Euclidean. Now, if you do it in hyperbolic, remember this is my environment that has the hyperbolic tools up here. We do the same thing. We just start with a point A, put anywhere we want, and a point C, and then we do a circle by center and point here from center A, point C. And so we have that. And of course, this is a radial segment. AC is of that circle, or AB is, sorry. We start with A and B because the A and B can be moved anywhere. And we can measure those distances using the tool for that up here, the hyperbolic distance tool. And then finally, I put in the angles and measured them as well. But though I finished it off by letting C be any point on that circle. So really, it's exactly the same basic construction, but this gives you an idea what these things should look like in Euclidean geometry, not in Euclidean, in hyperbolic. Here's the edge. I'm not sure why I lost some of it, so this may be a little buggy. So what I should have here is the line segment going across here. For some reason it's not letting me, not staying with me. Okay, taxicab. A taxicab circle, we don't need the edge here, looks like well, it is a Euclidean square and a taxicab square. If we're talking about taxicab, everything's related to the axes, so maybe we should have the axes on there. And so there's a circle. Again, we just built it using our taxicab circle by center and point. Pick a point that's allowed to freely move along the circle. That's our point. This again, A and B control the center and the radius there. Point C is free to move all the way around the circle. And so all of these are isosceles triangles. But notice on this one, it's something interesting. We don't get something that we do get in some of the other geometries, including Euclidean, is in Euclidean, these two angles would be congruent, and they're not. They're not the same here. In fact, you can probably make it where they're considerably different. So classifying triangles in other geometries is the same thing as classifying them in Euclidean geometry. We have exactly the same definitions regardless of which geometry we use for triangles and these different subclasses. So the basic idea is the same in Euclidean, taxicab, hyperbolic, and spherical geometries with exactly the same definitions. But even though we're using exactly the same definitions for these subclasses like acute, or obtuse and so forth. What we could do is go with the largest angle and see what size it is. But when we do that, line segments are going to look differently and measure differently in these geometries. So triangles will appear differently or might have different measures. So, for example, just one example of this, Equiangular triangles have a fixed angle measure of pi over 3 or 60 degrees in Euclidean and in taxicab geometry for all three angles, but they do not have a fixed angle measure in hyperbolic and spherical geometries. Equiangular triangles are always acute angles in Euclidean, taxicab, and hyperbolic geometry, but they always turn out to be obtuse triangles in spherical geometry. And we'll investigate these ideas in some of the homework tasks for later on the week. So here's a task that I'd like you to do on your own. Here's some links to some things here. The idea is to look at the sum of the angle measures, and we can do it by this here. So let's go to these here. So here is a general triangle here. This is one we did before, and we looked at the sum of the interior angles, and we see that it's always pi radians, 180 degrees. So you can actually measure them, have GeoGebra add those three numbers up for you, and see that it always turns out to be pi if you're in radians, or 180 degrees if you're in degrees. What about taxicab geometry? Well, it's the same thing. Here's a taxicab general triangle. We're measuring the taxicab distance and the angles. And once again, we see no matter what, if we add up those three angle measures, we still get, of course, same as in Euclidean geometry, pi or 180 degrees. Now, some other things are interesting about this. One of the things that you get in Euclidean geometry is that the smallest angle is opposite the smallest side, largest angle is opposite the largest side. That's not necessarily true in taxicab. Let me see what we've got here. So right now the smallest angle measure is 0.58 right here, and that is the smallest side. Okay, so there's about 42 degrees there, and this is 8 something. And this one down here is a smaller angle, 33 degrees, and yet it is the smaller side. Okay, so that's the normal order of things. So a lot of times it is like the normal order of things, but then other times it is not. So I have to just play around with this a little bit and see if we can find one where we have a bigger angle. So what do we have here? 46 degrees. So all right, here we go. Look at this one right here. This is 103 degrees. It's the biggest angle. The side opposite's almost 8, just a little under 8. But this little side right here is above 8, and it only has an angle of 50 degrees. So half as big, under half as big of an angle, but actually a larger side length when you're measured in the taxicab distance. That doesn't happen in the other three geometries. So that's something that's interesting about taxicab geometry that's different than the other two. Okay, let's look at this one right here. Hyperbolic. Here we have a hyperbolic triangle, and it's measured. And look at what happens when we add. I'm sorry, since the angles are measured exactly the same way in the taxicab geometry, the angle sum is going to be pi or 180 degrees for them as well. But look what happens in hyperbolic. Here we have the hyperbolic angle measurements in radians. There's one, there's another one. If you add those up, you get about 2.8 something. Well, see 2 pi, that's going to be bigger than, or pi is going to be about 3.14. So notice that's under pi, right? Under 180 degrees. And the amount that it's under is this amount here. That's called the defect. So it turns out, no matter what we do, notice that that number is always going to be less than pi. If we make it really small, we can get this to be kind of small, but it's never quite going to be pi. Getting close, but not quite. It's always a little bit under. So no matter what we do, our hyperbolic triangles there work out to be more than pi. Oh, less than pi for the sum, less than 180 degrees. And then if we look at spherical geometry, these are spherical triangles here. And I have, whoa, let me open it in the app. That always works better opening it in the app. So we move these around, you can see the angles again measured in radians. You can measure them in degrees as well. And they add up to what? Well, there's the angle sum. It's 3.7 something. That's bigger than 3.14, bigger than pi. So it's about almost 1.2 times pi. Okay, or in degrees that adds up to 213, almost 214 degrees, more than 180 degrees. The excess is pi minus that, okay, which is about 0.59053 over pi, or about 33.8 degrees over 180 degrees. So in spherical geometry, the angle measures add up to be more than pi. If we make it smaller triangle, then it gets closer to pi here, 3.1679, but it's still over by some amount, and the amount it's over is called the excess. All right, let's call it now on this video. We'll stop there. Next video, we'll talk about one of the most important things we'll talk about this unit is triangle correspondence and congruence.